I don't know if it's the software or what.
Never use Wirecast is the moral of the story.
It's terrible.
All right.
Week after week.
What's up, YouTube?
Yo.
All right, you're in. All right.
Okay,
All right.
so, where were we? Oh, yeah, we started, I think we got 2 seconds in to say, hey, we're going over comments for the last 3 videos.
All right, we gotta start all over, man, because a bunch of people watch this later, man. So what we're doing today is we got 3 investigates, and we're gonna dive into the things we didn't tell you. Questions that you may have asked because you did actually ask them. They're here on the sheet. We took them off of the comments. They're specifically designed to dig in deeper. We also have stuff from the cutting room floor. Maybe you want to know how something much cost because we decided to pull it out of the video, but you might want to know.
There's so many times where you just write a script like this long, oh yeah, and you write this long script for something and you think that all the information needs to be in there. Come to find out, it's just got to get cut. Yeah. It makes this, it makes the video a lot more clear, a lot more concise, but what happens to that cut material? We got you today.
All right, so for reference, we had 3 videos, investigates, we dug in, we found some science, we found some things that actually matter to how you maintain your tank. We found some pieces that connect the dots here as well. So we got the calcium reactor. I've heard a lot of people say that you add phosphate with your calcium reactor media.
Oh yeah.
It turns out it's definitely true.
It's definitely true.
Maybe a lot more than you thought.
The one thing, this is, you kind of know that it's true or you feel like it because you're looking, I don't know, when we ran the little coral skeleton bits for so long, kind of question always arose, like, why is there algae inside the reactor? Why does it look nasty, brown all the time inside the reactor? Well, come to find out, it's got 0.83, 200 times the amount of phosphates.
Right, that solution.
That's not out of the realm. Yeah.
We're going to talk about air versus water and how you measure PAR, but actually not even really that. We're going to talk about how you're going to use that data to produce a better result in your tank. And we're also going to talk about the human eye against PAR because we did all 3 of those investigates, but digging into your specific questions that we may have missed in there and people are asking. So let's dive in. So the very first one, I'll let you read it out.
All right, so first one we're talking about is the calcium reactor test. This one dropped yesterday, I believe, and people are all over the place about it. Like, are calcium reactors nitrate or phosphate factories? And some of the comments that rolled in, James says, always wanted an experiment that demonstrated the phosphate and or nitrate added per cube of frozen food in a set amount of water. Feels like knowing the inputs would help us all with the export. I 100% agree.
Yeah. So this goes beyond calcium reactor.
Yeah.
And it's on our list actually. Let's go and start adding cubes of food because I would like to know
dry food and like what the what ounce for ounce you dry out a frozen cube and you find out how many ounces or grams there are. Give that in dry food. What's the difference in phosphates?
So if I added 1 cube of food every single day for a month, and I did no water changes and there was no other uptake, where would the phosphate land? I want to know.
I don't know.
So in this case, what you kind of found out when you watched Randy's videos, a little bit of insight of different sources of phosphorus addition to the tank.
Yeah, it's not just food.
Food is definitely one of them. Nitrogen and phosphorus build up the DNA of food, or of organics rather.
Yeah, there's probably other sources of nitrate and phosphate. You think of like if you have a refugium or something, the breaking down of or the dying of some of the material underneath or the chaeto underneath.
Anything organic, it goes in the tank. Poo, food, algae, anything that breaks down.
Phosphorus and nitrogen.
Yeah, and and part of it though is understanding the scale because just saying it adds phosphate, shame on that thing. It's really not helpful. So one of them, I think that it was Stephen Pro who did this, and I might be wrong on this one, but I think that who it was. He went and tested carbon, and whether or not carbon added phosphate to the tank, and it's coal and stuff that came out of the ground in many cases, or peat moss or whatever, and it does. It has some amount of phosphate that adds. Now, at the time, this is like 15 years ago.
Oh yeah.
It sent everybody scrambling, like, oh my
gosh.
Don't use
carbon.
Carbon's gonna
Can
have
I get
phosphate-free
carbon?
Okay, the problem was what it was is they added 1 tablespoon of carbon to a cup of water and tested the cup of water.
Which, you know, in proportion to an aquarium and the amount of carbon that you need, not even close.
That means in my 100-gallon tank to get the same result, I'd have to add 16 gallons of carbon. Yeah, okay. So your 0.1 phosphate that you got out of that, I'm not sure that's actually relevant because I only use 2 cups of carbon, not 16 gallons.
Yeah.
Yeah, I don't know.
Very minimal.
But in this case, with the calcium reactor media, I think a actually shockingly high amount of phosphate coming from dissolving some of that organic material, or not organic material, some of the calcium carbonate sources, and dosing into the tank.
Well, the thing about it is too, and I did the math on it, at 30 mils per minute, 24-hour continuous duty dosing pump, you're dumping in, or you're turning over 11 gallons of water in a 24-hour period through your calcium reactor. Meaning that instead of just turning, if there was 0 phosphates in the media, it would just be whatever the phosphates are in your tank. You're not adding, you're not taking away from, you're not doing anything. But if you have the calcium reactor media that adds 200% more phosphate than what your water level is, then all you're doing is bringing low phosphate water in, dumping 200 times plus out.
Okay, for some of you that may not have seen this video, the coral bone bits, from tula fishes, when we dissolved it in the calcium reactor media, it was 0.8 parts per million.
0.83 parts per million, and the water source that was feeding the calcium reactor was 0.04.
Yeah.
So that's a lot.
A lot. Yeah. Yeah. Okay. And it's funny because that was the one that we really liked because it looks most like a coral.
It
seems
sense.
like kind of closest to the application.
Yep.
But if you wouldn't watch it, you'd say, I'm not sure I would use that one. No.
Yeah.
In fact, no.
Yeah.
So interesting. I'll bring up the next one here, which is great test. The reason for the difference in the high pressure and temperature changed relatively soluble calcium phosphates into extremely insoluble fluoro and hydroxy apathates. The higher the pressure, the temperature, the more insoluble the forms of phosphate. And what this is getting at is, in that experiment, there's, you think of calcium carbonate as just calcium carbonate, but it actually comes in different forms. Like limestone's calcium carbonate.
Oh, yeah.
Coral skeleton is calcium carbonate.
Yep.
Marble is actually calcium carbonate.
Dolomites, all kinds of different forms of it. Well, this is with my argument at the end that, why would 3 aragonite-based calcium carbonates have phosphates and 1 calcite? Does that mean all of them are going to be the same? No, but you look at the density, the structure, and how it was made. The coral bits closest to the thing that was actually living just a while ago, because it still looks like a little piece of coral, probably still has a bunch of phosphate bound into the skeletal structure, something that you mine from ancient coral beds that could be thousands of years old or millions of years old that you're mining from the ground, ancient ocean. Probably because of the higher temperature and higher pressure over the years and decades, could have turned that phosphate insoluble.
That's what David Bogart is saying anyway. So here's the
plausible.
The interesting piece is why would the coral bits that actually looks like little pieces of acropora have higher phosphate in it, or why would it have phosphate at all? Right? And it's the same reason that we keep phosphate low in the aquarium, because what happens is, as the calcium and the carbonate are coming together and they're forming calcium carbonate to build that skeletal structure, what's happening is the phosphate pops right on the end of it, and we call it poisons the surface, because now it doesn't have an electrical charge that actually wants to pull in more calcium and carbonate, and actually repels it. And so it stops the coral from growing actually at that site. And eventually stuff will grow over it and around it, but if you got too much phosphate, you end up poisoning the surface of so much that it actually makes the coral grow really slow. And that's one of the biggest reasons we want to maintain low phosphate in the tank. But it happens in the ocean too. And so in the ocean, you're poisoning the surface of that little coral bed in there just from the natural amount of phosphorus in the prey or the surrounding water. And even though it's lower, it's still getting incorporated in the skeleton. And so when we melt that skeleton back into the tank,
phosphate.
Boom, add phosphate.
Well, it's like you think of the compounding nature of this process of I got a little frag and it's getting some phosphate on there, and then eventually it'll grow into a mini colony, but it's building on top of phosphate, building on top of phosphate. So the real question is, by the time that it turns into calcium carbonate, or calcium reactor media form, where it's all dead skeleton and dried, and you're putting it now in your reactor and remelting it, does the phosphate live only on the surfaces of that media, or is it all the way through to the center?
Yeah, I think it's probably throughout the entire thing as it's been poisoned and grown over.
Yeah.
I think there'll be an interesting maybe escalation of the test here, but let's go on to the next one here. Ryan Thompson said, over the years, the best tanks I've seen seem to run calcium reactors. I highly doubt adding a little PO4 is hurting anything. A lot of us have to dose it or overfeed like crazy to get PO4. If I had a calcium reactor running, I wouldn't pull it off after seeing these results.
No, I wouldn't either.
This is a good, a good comment from Ryan, because down when we were at Worldwide Corals and we were viewing all of their tanks, I picked up on something that was kind of surprising to me.
Yeah, they not only are dumping a bunch of food into the tank, but at least once or maybe even twice a day, they're taking Brightwell Phosphate E and dosing it into the tanks as to control the higher level of phosphates. And you're wondering, like, okay, well, is it the amount of food they're feeding, or what is? It's not the filtration, because they're, 2 times a day they're pulling filter padding out and putting it back in mechanically. They've got big giant skimmers running. The coral biomass itself is soaking up a lot of this. So where's all that phosphate coming from? And then you go around the back and you start to look at how they're fueling these tanks with calcium and alkalinity, and it's big giant calcium reactors with ARM media.
Okay, so that was the 2 pieces of the puzzle for me. Is what they said was, we have stable nitrates here. Like, the nitrates aren't continually growing. We keep them somewhere around 20 in many cases, but they're stable. But we have to use this phosphate E to be able to pull the excess phosphate out. And I'm like, well, why does phosphate keep rising, but nitrate you found to be stable? And I didn't put it together at that moment in time. It was later, like, it's because you have a different source of phosphate, being the calcium reactor media going into the tank.
So it's like unbalanced with the amount of nitrogen and phosphorus that are in the tank.
And they're burning through media in this case. So it's adding a lot. And so, but the flip side of this is, like, that might sound bad. And, like, if you watch this video, you'd probably say, like, oh, I don't know if calcium reactor is for me. And Ryan Thompson came out here and said kind of the opposite, like, this wouldn't stop me from doing that, which I bet you is a rare viewpoint after watching that video, but also an accurate one, because all they do is strip some of that phosphate out using the phosphate E. And the reason that they use that one is because if GFO is kind of like, it'll just take it all out.
Well, and not really, easy to measure. Like, this amount of GFO is going to have this result.
The goal is to put enough in that it takes it all out in most cases, and then keeps it there as well, right? Whereas with the phosphate E, because it has like a known concentration, I can dose some, if I dose 50 milliliters of this tank, it would lower it from 0.1 to 0.05. And it will do that every time I do that dose in this tank. So it's really reliable and consistent, and makes it a lot easier.
Yeah.
All right, so next one.
Louis says, I really have a problem keeping my nitrates up. My phosphates always climb up and I need to run GFO. It's always been strange that I lose the balance this way. Maybe my calcium reactor is the problem. I've always stayed away from the hard media because of the low pH melting point. Seemingly, this is exactly what this experiment is about.
It hits everything that you tested.
Yeah.
Right? So almost certainly the fact that phosphates are going up way faster than you can control, but nitrates aren't, you have a different source. You're using, it sounds like bits of coral in this case.
And you didn't want to use the other media because of the low pH melting point it takes to dissolve that more thick crystalline structure.
So I'm going to actually share a thought process they would share with me that you got to decide which end of this you're on, because it may or may not be true. But like, I had a friend of mine, Max, who owned a maintenance company locally, and he said, I would never use a calcium reactor because for one and one only reason. As aquarists, we spend so much time trying to get the pH up. We have such a problem with all the excess carbon dioxide in the rooms from us breathing. By the way, we did an experiment on BRS. I don't know if you've seen it yet, but we bought a calcium or a CO2 monitor
somewhere.
Yeah, it's in this room. And when you see the difference between the weekend, when nobody's here in the weekends, you'll be floored. And it shows up right up into the pH of the tank as well. So why in that world where I'm having all these problems keeping the pH up, and then when we find out that the corals grow twice as fast if we actually keep the pH up, would I put any piece of equipment on the tank that intentionally lowers the pH with a low pH fluid?
I know. Well, I mean, all that's going to, well, all that is going to spur. I mean, I agree. Yeah. Like, why would I fight fight pH? But that spurs more experiments. Okay. Well, rather than just say I'll never use a calcium reactor, what are the different ways, or what are some of the best ways that we can mitigate the low pH but still get all the calcium reactor benefits?
So here's the answer to the flip side of that is if you don't have a pH problem to begin with, this isn't part of the equation.
No.
Like say that you live in a big house alone. Well, CO2 probably isn't a problem. If you live in a small house with 6 kids, it probably is a problem.
Right.
5 dogs, then it's going to be a problem. So it may be a problem for some people in a way that it isn't for others. But if you're already having a problem, why scale it up even more? But also, like, it's the type of tank. So if you look at the worldwide corals tanks, I mean, end-to-end coral.
Oh, yeah.
Right? There's so much uptake for carbon dioxide in the tank, so many living organisms in the tank that are using that for photosynthesis. It's just not a problem.
Yeah, pH, when every single piece of zooxanthellae in a fully jam-packed SPS dominated system is creating or pulling CO2 from the water, creating a better balance, why not? But I wonder if you could run this is one I really want to try. Is like, okay, so we have this pH problem. Let's set up a tank that has the effluent running into a refugium. Let's set up a tank that has the effluent running into the skimmer input or the recirculating skimmer input.
What would be interesting actually is if you took the calcium reactor, took it one step further, and then put just its own little CO2 scrubber on the end of it, right? Just whisked the water and air together and just stripped it out.
Well, I already did the test of, does the secondary chamber on a reactor off-gas CO2, and the difference was 6.45 to 6.42, so hardly at all.
So here's the big deal
Or
here
vice
is
versa.
why you're going to see so many people out there raising their hand oh, it's not a problem for me, and for other people oh, it was a problem for me, is because it's that difference. There isn't a one size fits all answer for everybody. If you have 6 people and 6 dogs living in an apartment, it's going to be a bigger problem for you than a much larger house with one person in it. So think about how all this stuff applies. So next one here, great video, mind-blowing results. Does the phosphate concentrated on the surface area as left behind by an animal died, or is it binded deep into the calcium carbonate structure? Is it possible to test and answer that? Meaning, when we got those little coral bits and then the 8.4 phosphate that came off of it, was that organics on the surface of the coral, or is it bound up in the skeleton? Because with those harder types of calcium carbonate, what were the 3 types?
There's aragonite, calcite, and vaterite. But aragonite and calcite are what we use. But
yeah, so the calcite's so hard and so dense, it's clearly been mined or something like that. It's doesn't resemble a coral in any way.
Yeah.
Right? So that calcite stuff was doing either 0 addition of phosphate or very little, right?
Yeah. But even different than that is the two other forms of aragonite that had phosphates. I mean, they look nothing like skeleton bits except for arm media that was the middle of the road. It actually it looked like fossils. You can still see little shells and stuff in there. So it was definitely from an ancient seabed, but with like 40 times less phosphate than the actual coral skeleton bits. But he asked the question, is it possible to design a test to answer that? And I actually think that this one's pretty easy. That you, just like we did, I filled up a reactor, I fed it, and I ran it at a pegged pH for 24 hours, and then tested the phosphate. If we were to come back about a month later after use, you would think that all of the surface of all the little bits were now dissolved away, and we'd be working with more of the middle of the material. Would the phosphate stay the same all the way through like 2 or 3 months worth of use? If they did, then it's probably bound all the way through the material rather than just the surface.
I agree.
That's how I'd test it.
I believe wholeheartedly, though, looking at the stuff, it looks pretty clean. I don't think it's from the organics. I think it's poisoned in the surface of the calcium carbonate crystal and melting. All right, so Julie Morgan, my nitrates are 0, phosphates 0.25. How do I lower phosphate and raise nitrate? Those are two different questions. The best ways to raise nitrate is feed more or reduce the efficiency of your filtration, I guess. You could turn your refugium on only every other day or 4 hours instead of 8 hours. You could feed more, you could turn your skimmer off for a portion of the day, or you could actually dose actual nitrate to the tank. I think the most popular one's from Brightwell.
Neonitro.
Neonitro, yeah. Okay, but how do I get my get the phosphates down?
But raise nitrates.
Okay, well, there's all those inverses, make your filtration work better, but these are like the opposite of what we just said, and it's not going to help you. So what you're going to have to do is strip it out.
This is one of the times where you could use GFO as a tool to get you back down, get you down to the level where you want to be. And you can do it that way, but at 0.25, that Brightwell phosphate E stuff is measurable, and it says it will bring down your phosphate like by 0.05 or something with a certain amount of dose. Well, and now I just know I dose this much.
All right, I'm going to defend GFO for a moment. Because I just recently started using it again. I don't really use GFO that often because I don't have a phosphate problem. But at my tank at home, I was feeding a lot, trying to keep a bunch of anthias alive and stuff. And so I was feeding a lot, and I was starting to get creeping phosphate in it. And I was like, you know what? I'm just going to put some GFO in with the carbon that I run all the time. And what it did is different than what I had done in the past, which is I didn't put so much in there that I was designing to keep the phosphate like at really ultra low levels all the time. What I did is I put enough in there that it brought it down to where I wanted it, and then it was depleted, and I let it kind of creep back up before I used some more. So instead of using so much that it's like trying to strip it out and keep it there 100% of the time, I didn't have problems with algae or anything like that. It was just the health of organisms and trying to keep stop poisoning the surface of the calcium crystal. So. Yeah, I actually use GFO a little bit different, a little closer to how you might use phosphate E, I guess, which is use some of it to get it down. And if I actually paid attention to it, I think I could get the same effect, which is I could figure out that a cup of GFO
mixed into your carbon,
mixed into the carbon would reduce it from 0.1 to 0.5.
I bet you could.
And I just know that
when it gets back up, do it again.
Presumably, too, if it went up from 0.15, if I used 2 cups, it would go down to 0.05. So I think you could use it that way in a way that I haven't used it before and really kind of got the juices flowing for me a little bit.
Yeah, that makes sense.
All right, so the part that we cut out was actually pretty interesting to me because sometimes the most expensive options out there are the best, and sometimes the cheapest options are the best. I'm dying to know.
Such is the case.
So there was 4 different medias here. The Triton media had no phosphate in it.
Calcite-based.
Calcite-based, but the pH had to be pretty low, like 5.9.
Yeah, 5.9, pretty
low.
To
get a 30 DKH effluent. The 2 little fishes, you could go all the way up to 6.5 to melt it, but it added a lot, 0.85 phosphate.
Tons of phosphate.
ARM, a little bit better. And then the KZ media was kind of like a blend of both, 6.1 and just a tiny bit of phosphate.
Almost unmeasurable given the tool and the variance and the range of it. So you could almost say none to very, very little amount. No, but in the end, like the ARM media, it melted at 6.1, but it had higher like 7 times the amount of phosphates.
So what was the cost?
This one's pretty interesting.
Do you have the sheet?
Here's the sheet. So the cheapest option, being the $2.48 per pound, is KZ aragonite media, which
shocking.
I know. So this is why the reason you said you were going to ask me this question, and I cut this part out. But this was another part of the reason why I said, if I were going to choose a media, I'd choose KZ. One, because it has 6.1 melting point for 30 DKH, which was like the ARM, but the ARM has higher phosphates. It's not as good as the Reborn, but it's way less phosphates, and it's not as good in the as the Triton in phosphates, but it is higher in the melting point. So KZ, Ragonite, $2.48 per pound. Next up was the ARM at $2.55 per pound. And then Triton at $3.18 per pound. And Two Little Fishies at $4.05 per pound.
So if you had asked me, I would have told you I've never seen anything where KZ was the cheapest of anything.
Yeah, that's true.
I would have been really surprised. I also would have been surprised that Triton wasn't among, they would have come in number 2 either.
Yeah.
All right, so you guys do what you want to do with Calcium Reactor Media. You now know more about it specifically. I watched this video again this morning, and I texted Randy, and I'm like, dude, you did a really good job on this one, because the measurement I'll put this on is, you have changed the way that I will think about Calcium Reactor Media forever. I will never think about it the same way again.
I think so. The revelation for myself in this one too.
Yeah. So bravo to you. It was the first thing I did at 7:30 in the morning. Watch this thing and share with you. All right. So next one. Okay, so we got a bunch of questions about testing PAR in air versus water.
Yeah. Oh, this came up with a really good conversation, because a lot of times on manufacturers' websites or other people in the industry who have PAR meters and things like that, they set up these tests for lights, and it's like, all right, we're going to measure PAR, the PAR output of this light. And especially when you're making comparison videos of how it compares to another one, but also from a manufacturer's standpoint, this is what you're saying your light can provide. The problem is a lot of times those are measured in air, and air is just not representative. One, it's completely disrepresentative of how we're actually going to apply it in the real world environment that it's made for. But the properties of light in a glass box with water dramatically changes the output.
So I'm going to tell you the outcome of this, in case you didn't watch it, was overwhelmingly you should test this in water, no question.
Always.
And I'm going
you
to tell
should
you,
ask that question when you're looking at PAR charts, or you're looking at PAR data from any light manufacturer or anybody that is kind of giving you the rating. You should ask that question: was this tested in water or air?
Here's the thing. This is the reason why this really came up for me, is I got a little bit of a pet peeve with this one.
Yeah.
Okay, so testing in air, meaning in testing for air versus water, for anybody not following around, testing in air means I get a little 2-foot grid, and I take a 36-point or something like that grid in air. I usually mount the light exactly 24 inches or something above it, a fixed light. There's a couple of problems with that. One is an enormous amount of light spills outside of this 2-foot area. It's just not captured. The other is it's like 2 foot away, so it's a fixed height for all lights, even though some lights are designed to be like 6 inches away from the tank, and some of them are designed to be 14 inches.
14, yeah.
Like putting them all at exactly 24 inches
doesn't work.
It just, the mindset here I understand, because what we're trying to do is put all lights in the exact same environment, and we'll all measure them all against this exact same thing, remove all of the interferences and
variables,
But we've done it so much so that the same fixed height and the spill, it just doesn't give us a representation of anything.
I think that's like going to the car dealership, and then the car dealership has this little off-road ramp, and then you go and you want to take every single car through that off thing, and then go up. If they don't, here's how they all performed. But they're not made that way. This little red sports car is not made to go over that thing. Mm-mm. This little one's made to go over, dirt trails, roads, what have you. So
it's just crazy.
You can't have a standard like that. But
so this is my pet peeve. So some of you, this is how ancient I am. This goes back to the halide T5 thing.
Yeah.
Okay. And like back then, everybody was talking about punch. You know, you need to have punch to get the par to the bottom of the tank, you know? And so we're all testing these things in air, and you would look at it and a halide would perform really well, and halides have that punch, and like your mentality is like, I got this super bright bulb, of course that thing's got the punch to get to the bottom, you know?
Yeah.
And then I got these T5 lights that are performing terrible. Right, like they don't get any par to the bottom. The results are like really dismal. T5 lights too soft,
Inferior.
doesn't have the par, punch, whatever. But
actually, I remember that was the advice for like if you want SPS, you want SPS dominant, halides. T5s can't do it.
Two T5s are inferior. We now know that to be a total joke.
Total joke.
So that's why it's like using this method made the entire hobby come to a completely wrong solution. Right?
Yeah.
That like just wasn't accurate at all and made us do the wrong thing, right? Now, when you fast forward and you put the T5s in an actual glass box of aquarium, instead of having that super big wide angle light that has reflectors that sends light out super far, instead of just spilling it all over the floor like it did with the air test, the glass, if you watch the video, reflects it and refracts it back into the tank. And then that punch comes from not just the rays down, but all of the reflections that go back down to the bottom of the tank. And I'll tell you that it's true too, not just in our testing, but in real world tanks where we actually go measure the par down at the bottom, and it's definitely brighter. 250 watts of T5s puts a way more light than 250 watts of a halide bulb, and not surprising because the halide bulb put out so much heat we had to have a chiller, and heat is just like a measurement of energy inefficiency.
Yeah,
like, it all comes together. But testing in air, like, made us all come to the wrong conclusions. So that is why this is the biggest pet peeve for me, and why now, actually, really what happens now is when you test in air, it like, you know, makes these like laser beam lights with super duper focus lenses look better.
Yeah.
Right? And then you take all the lights that are wide angle and had hit objects from all kinds of different angles, as well as off the reflections, that perform better at the application of an organism that requires light to provide energy, and it punishes that light by allowing it to spill on the ground. So obviously this is a pet peeve of mine, but like understanding this now, if you go watch the video, you're like, oh, I get it. I get why this glass is doing that. All right, so read the first one.
All right. So, water versus air test. One of the first comments that came in questions was, awesome information. I didn't realize how much water amplifies the par. That's crazy. It doesn't amplify it.
It doesn't amplify it. The water won't make the par go up.
Bigger. No.
It just takes
takes
that light that was going to go through the sides and spill on the floor, and bends it, or refracts or reflects it back into the tank. So it essentially like captures all the light. It doesn't really amplify it or make it more than it was before. It just captures it all inside that glass box. And what's kind of interesting is like, I didn't expect it to be so pronounced. When we brought out the laser and there's no water in the glass and the laser goes straight through the glass, when you put the water in, all of a sudden it bounces back in. Right? And it was interesting because I actually called up a bunch of my scientist buddies and like asked them all why it does this.
We were talking to Dana and we were talking to everybody,
And everybody didn't actually know. You know, we talked about Schnell's law and stuff like that. And then what actually came up is we found a video or an article about why I can't see my watch underwater at certain angles, and other angles I can.
I read that.
It looks like a mirror in many angles. And what's happening is the light's actually passing through the glass, but it's hitting the outside edge of the glass, but the glass changes refracts the light and bends it at an angle that makes it bounce back in. And the only area that it doesn't bounce back in is the very, very, very top. And it's interesting because when we got the laser out, it didn't just like shoot through the side. It went through and it refracts so strangely through the glass, it shoots down at the ground.
It's crazy.
You know? And then you're like, well, I can actually see that with my eyes at my tank when I look down and there's light on the ground.
There's light on the ground. And then when you're looking at your tank up against the wall and you see the actual shape of your tank up against the wall, you see, oh, that's all of the light bouncing off of the top of the surface of the water.
Yeah.
The laser was so much fun.
This one was interesting too. Practical reefer. This is incredible. Assume the manufacturers put par and air values as an attempt to make the lights look better.
Yeah.
But they're actually making them look worse.
Well done.
And it's true.
It is true. It's like if you, especially for those that build those very wide angle type lights. So you think if if the Neptune, the Radions, these wide angle lights that we've been testing recently, if they give you the data in air, it's going to look just muted. It's going to look less par. You're not going to see you might see the actual spread or the more realistic spread, because it's made to, you can see, oh, well, there's still par out in the outer 36 inches. But you're actually, if they did that way, they're doing themselves a disservice, shooting themselves in the foot.
All the manufacturers that are testing air are actually underrepresenting how the light's going to perform in the intended application. So it's actually interesting. I would have thought the same, actually, without really thinking about it too deeply, that the air would perform better, and that's why they do it that way.
They're doing it in air. That means it's going to be better.
I think one of the number one reasons they probably don't do it in water is because nobody wants to get their arm wet. Actually, I've seen it though at some of the organizations that do this. They actually do it in air, probably because what they do is they have a little robot that sends the probe back and forth, and it will so you can go push a button and it'll just map out the par.
Yeah, you can't do that underwater.
Yeah, they don't have a Brent that has to go into the water
he
to do it
every 2 seconds.
Getting
write
a robot
down the
to
numbers.
work underwater is harder.
You only got to do it once.
Next one.
Cool Jewel says, BRS discovers this is funny. Little tongue-in-cheek here, but BRS discovers the basic physics of light. Funny part is, many experienced reefers are floored by the results. This is high school physics, folks.
It's true, actually. But you know what? I actually reached out to a bunch of scientists in our industry, and they didn't know. Some of the people that actually test lights, and they didn't understand what was going on either.
The confusing point is like, yes, we know the physics properties of, the refraction, reflection, how light, when it hits water, it gets bent and all this. The variable here that I don't think really much testing exists on is how light reacts in a box of water. Like a glass box of water is a completely different variable than anything that, why would a scientist go explore glass reflections, light reflections in a glass box? It's just doesn't apply to hardly anybody, but for us, it applies massively.
So I don't know. For the person that's researching this, sure, basic physics. But if you take the laser and you watch it go through glass flawlessly, almost none of it gets reflected back into the tank, and it goes right through the glass, and then you fill it up and you see the exact opposite, that when the thing is full of water, the laser no longer sends water or light out of the tank, and you can see the beam just bounce around in the tank.
Yeah.
Okay, well, bravo to you that you knew all of this, but to everybody else in the world, you can see how profoundly well the glass box holds it all in.
I mean, we've got a pretty good understanding of, some of the science basics and things like that. But even when you and I first took the laser back there and we saw this firsthand, we were sitting there holding papers, looking for where the beam went, doing all this other
Smoke
stuff.
machine.
Yeah, we had all kinds of stuff. We want to figure out what's happening to this thing, and we were just floored that it was acting so strange than what you thought.
Well, and so for us too, it's not lost on us that we're creating video, and so having a visual element like the laser show you exactly what's happening in the. I can connect the dots now in a way that just pure par numbers doesn't.
Yeah.
I can connect the dots as to what happens on the black back of the tank. We'll talk about in a second. But I get it why it's showing this way in a visual representation that makes it a lot easier to digest. One of our most highly decorated commentators on our videos, Shaozin Zhang, I believe is how you say it. But water test is a great estimate if you have the same size of tank. But air testing is more useful to identify the physics of the light. If you just test a 24-inch cube, but not test a 40, physics of light in a 24-inch cube versus a 48-inch cube.
The water performance in a 24-inch cube could be estimated by folding the values outside of the preliminaries back into the tank with a coefficient. The same could be done with 18 and 32 widths. This is one of the data could be useful in the scenarios, though some additional work.
Okay, I like the thought on this.
Like, could you take the data from a 24-inch, flip it, add some coefficients, add it to a 48-inch?
So what this is getting at a little bit is that, yeah, okay, so the glass box changes the dynamics of the light, but also not everybody using a 60 cube, but if I had a 30 cube, but if I had a 120, the physics of the light won't be the same, it's gonna throw it off, all of which is true.
Yeah.
Right? All right, so what he's saying is, well, couldn't you just get like a 40-inch grid and then, use some kind of, coefficient or calculation to fold that light back in to the shape or size that you had. I don't know, but that's also way beyond what anybody's gonna do.
That we have a Brent that goes into a 48-inch tank and tests. And not only that, but like when you're extrapolating some of this information to a 48-inch tank versus a 24-inch tank, a couple things happen. In a real-world application, I'm using more than one light to cover that area. And that introduces a whole other different type of variables with intersecting points of light inside the tank. The how this one light over here bounces way the heck over there, but how that also blends with all the light that's coming back this way. The reflection and refraction beams inside a longer tank with multiple light sources is probably 100 times more complicated than a simple beam inside a small.
Yeah. So here's the answer to that story. Of course it is different in different sizes and shape, but we chose a 2-foot cube because most of today's LED fixtures are designed to be optimal over a 2-foot square.
Yeah.
So it makes sense that maybe like 80-20 this, like help 80% of the people. And like a 120 is a really common size. And even if it deviates from that, like it's a 90, it's still 2 feet by 18 inches that it's probably gonna cover. It's not that far off. And then things like the prime, there's a reason why we tested it in an 18-inch cube instead of a 24-inch cube. In fact, in that one, we actually tested it in both, so you get an idea. So somebody actually asked this question too, is because none of these options are perfect. Air isn't perfect, the water apparently isn't perfect, it's not the exact same glass box. But the person that responded to that question said this: yes, it's not absolutely perfect to test in water, but that doesn't mean we have to pick the absolute worst option instead.
That's true.
And by worst, I mean like the par that came out of, I think the Red Sea 90 was 130% different in air versus water at the bottom. It was like the difference of 60 par to like 130.
That's big.
Dude, it's not even the same realm. I would pick, if you made me buy a light based on that performance of 60 par in air, I wouldn't buy it.
Yeah.
Right?
It's not going to meet my needs.
With 130, I know that this is actually a pretty solid LPS light in my 2-foot area I'm covering inside a glass box.
So don't pick the worst testing option that we're stuck with. Pick one that's better, may not be perfect.
Yeah, or figure out the coefficient calculation over a 40-foot area. I mean, I love the fact that he said this because it's next level thinking.
Yeah.
But I mean, I'm trying to imagine, like, the average person would never do that. Could we do it, in a 40-foot or 40-inch area? The problem would be like proving that was accurate in every possible formulation of the calculation and really being confident in how you could fold par back into a box.
We're talking a month or two worth of testing to come up with that formula to do that when just got some part meters.
Okay, you know what? Actually, one of the other things about the air test and like the fixed height of 24 inches is it actually only tests the worst possible point at which wide angle lights perform, which is the bottom, right? And so with the water testing we're capturing the bottom, the middle, and the top, and we're seeing the distribution. And when if you did that in air, with the lights that actually perform really well at the bottom, if you did the test at the top, you would see it's a total laser beam.
Oh yeah.
Right? It's like 800 par, right, at the top. So like the one that performs the best in air at the bottom will probably perform the worst at the middle and the top.
True statement.
Yeah, so pet peeve.
There's a comment on here. Christopher says, maybe we should just take the blue pill when it comes to the cube of light.
Oh, yes. So funny.
Dusk 194 says, I've said this before and I'll say it again here. Your light testing methodology is a standout for the aquarium lighting technology. Is it perfect? Is it without improvement? No, nothing ever is. But your methods present a standard which producers should attempt to meet.
You know, it would be nice. It doesn't have to be our method necessarily, but it'd be nice if everybody tested.
Thought a couple steps higher on.
And I know that that's the perception at testing errors. It's equal, but it isn't. It doesn't. We're not testing at all levels. We're not testing at the recommended manufacturer's height from those levels, and we're not even attempting to capture the fact that this glass box holds it all in.
Yeah.
We're just throwing all of that away. So that doesn't make any sense.
Weird.
All right. So, all right, Christopher Crawford. So I'm imagining what it would look like standing inside the aquarium looking up. Would you see the actual light above you, but also a reflection of each light in the pane of glass unless it was painted? You might also see as many as 5 lights, the real one, and 4 reflections in each glass pane.
This is really cool. Before we talk about some Snell's Law and things like that, but what I did do, in some of my testing was I couldn't find an experiment online or an explanation for why it is. But if you you find yourself like a square container, a glass container. Maybe it's a small aquarium, but something with flat sides that is like your aquarium. If you put like a knife or a straw down into that, and you look down through the top at one of the edges, you'll see a mirror image. You'll see the straw inside when it's full of water. When it's empty, you won't see anything. But when it's full, it turns into a mirror. And same thing here is what he's saying is like these glass sides then turn into a full mirror. And not only that, but it also has something to do with the same principles that apply to like one-way glass. So a one-way glass is typically a very bright room on one side, a dimmer room on the other side, the angle of the glass inside the bright room, and they do put like a film or something on there to help reflect it back. But if I'm sitting in the bright room and I'm looking at that piece of glass on the dark rooms on the other side, just like sitting in your house at home with the lights on inside at night versus looking outside, like you see yourself. Same thing in a box.
So this is my opinion what would happen. I've never stuck my head inside of a glass box of water before.
I might have to for science.
But somebody asked the other day, is like, I can look through the side of my tank and I can see a reflection of the fish. Are the fish seeing a reflection of themselves? Okay, so here's the bit you got to really consider is, the answer is almost certainly if the fish is looking out or if you put your head straight out, you would see the room.
Straight, outside. Like 90 degrees.
The nature of it is glass is transparent. If it didn't allow light straight out of it, you wouldn't be able to see the coral.
Right.
Because the light's hitting the coral, bouncing off the coral, and then back at your eyes.
When you start to look at an angle, though.
Yeah, if I was down deep and I was looking at it, I would start to see not just the light above me, but I'd see the lights in the angles around the tank probably as well. So you probably wouldn't be looking at a bunch of mirrors, but it depends on the angle. But for the most part, if you're looking straight at something, it's kind of like when we shot the laser into the water. If you shot it straight down, it would shoot all the way through and keep a straight trajectory. But when I turned it at an angle, all of a sudden it takes this weird hook when it hits there and refracts off the glass as it goes from a fast medium to a slow one. So yeah, I don't know. Very interesting.
That is interesting.
All right, we got a couple more on this topic, and then we got the par versus eyeballs.
How crappy your eyes are.
Yeah, this one was actually really interesting when we did it. All right, next one.
Patrick, on the topic of air versus water, I think this was a fair way to address the issue with testing. I think air testing and water testing have their own respective benefits. Sure, biofouling on the glass needs to be taken into consideration, but even with biofouling, I would wager that the majority is sent back into the tank and not absorbed by the dirty glass.
Okay, two pieces on this. So the question is it fair to test in water if the glass is dirty? Okay, so I've seen this pop up as a rebuttal on many of these things, right? Well, yeah, dude, if it's filthy, then it's not going to reflect light the same way, but I'm also not going to want to look at my show tank through a filthy piece of glass. So yes and no. Like the way that you would actually look at this tank or have it in your house, it would probably not have the same exact properties, but like in a real world application where I want my super awesome tank to look super awesome and not dirty, I don't know. And the other part of it is, this was really interesting because I did not see, this is the part of the physics I did not expect to see. So glass has a thickness. It, could be a 1/2 inch thick, it could be a 1/4 inch thick. And I expected what would happen is the laser or light would come down, hit the glass.
Inside pane.
Yeah, inside pane, and then refract back off, in which case it'd be hitting like the dirty glass, I guess, right?
Yeah.
But what's really happening is it's passing through that surface, hitting the outside edge, and then bouncing back in. And the way that you could see it in the video that we produced is you could see the in and the out. It doesn't have a hard angle where it bounces in and out. The out
travels through, continues the path, and then comes down.
It's about as far apart as the thickness of the glass.
Yeah.
So with 1/4 inch glass, the in and the out are actually about a 1/4 inch apart. 1/2 inch, it's about 1/2.
And not only that, but then when you guys, I don't think it was in your video, but when you and I were doing that on a tank, we were pointing the laser at the side of the glass, and then at the bottom of the tank, on the black bottom, there's 2 dots.
Yeah.
It's like one line coming in, hitting the water, refracting down this way, hits the glass, comes back out off the glass, and now it's separated into 2.
There's one really strong one that's going through the glass and bouncing off.
Yep.
But a little bit of that light is actually reflected off the inside too.
pane.
And you can see a second little dot, and sometimes a third one.
Probably 80-20 though.
Yeah, at least.
Yeah.
Way more is going through and bouncing off. So it's actually not the dirty end. The dirty end could actually prevent that. But the real question is like, do I keep my tank clean? If the answer is yes, this doesn't apply to you. If your tank is filthy, this definitely applies to you.
Yeah,
I don't know.
That's true.
It's a very interesting question. All right, Justin B. Great video. It would be interesting to see the difference between the reflection on the bottom of the tank. Does the glass and bare bottom reflect more or less light onto the sand? Did you guys test in RODI or salt water since the refractive index in air is 1.10 and RODI and 1.32 in salt water? So the answer is, or the question really here is like, would the bare bottom actually reflect more light than like sand, white sand? In this case, I think what they brought up before is actually applicable because bare bottoms are always dirty. They always have coral, junk, everything's growing on them. So,
a lot of times ABS too.
Or black.
Yeah.
In which case, definitely no. Or you painted it bottom black, which we'll tell you in a second. Definitely no. So I don't think that you could use the argument that a bare bottom glass is actually going to reflect more light in the end in an actual application because you're not going to keep it clean the same way you keep the sides clean.
And I saw another part to this question because there's a couple different things that he's talking about here, but one of the things was that refractive index. So air being 1.00, water, RODI water being 1.32, and salt water being 1.35. To me, that says, okay, in air, there's no refractive index. The beam comes from here, and it continues on that path until it hits the table or what have you. Water has a 1.32, where...
fresh water's 1.
Fresh water is 1.
And salt water is 1.32.
Okay. Anyway, so when it hits fresh water, it has a little refractive index, but then it comes down. Does that mean that salt water being a higher refractive index, the beam comes down and bends even further? Yes, but probably not to a degree where it would change the par numbers, or you could actually see the difference in the laser beam. I don't think you could.
You might be able to see the different laser beam if you really had it side by side. We tested it in fresh water versus salt water because we used to do it in salt water. And the problem is the salt water would actually grow like bacterial films and blooms and stuff in it.
You couldn't get very many tests done before the tank was cloudy, and it skewed the results from the par meter.
If you did it on Friday and then you came in on Monday to finish, you'd have to like empty the tank because it had this weird gunk in it. And so in the end, we're like, well, let's just see if there's really a difference here between freshwater and saltwater. And we did a grid of par measurements, and we couldn't get any measurable difference.
So now we tested fresh.
Yeah, so I couldn't just, there was no noticeable difference between them. And why are we going to mix up saltwater, maintain it, and constantly be switching it out if it doesn't make any difference? So we test in freshwater, by the way, and that's the reason why.
He also makes the point here and asks the question, are you heating the water as refractive index is temperature dependent?
Yeah, again, it probably does change it just a tiny bit, but not like the same effect of capturing all the light and refracting it back in. So no, we don't heat the water to the exact temperature that you would have in a tank, but it's also not terribly off because it's 70 degrees in this room. So, you know, it's 8-degree difference. You can decide for yourself. I don't actually know the answer to that question. Like, I've never tried to heat the water to see if it dramatically changes the angle.
I don't think it's much.
I think it might change the distribution of light a little bit. I mean, by a little bit, I'm not sure even measurable, but it won't change how much light like passes through the glass, I don't think, or anything like that.
Yes. All right. Go Asky says, notice the par values are lower in the back half of water filled tank due to the light absorption by the background. Great job, guys.
Okay, if you've watched any of Randy's work on BRStv Investigates,
all of them, yeah,
you'll notice the back half of top, bottom, or the top, middle, and bottom are always way darker.
Yeah, and the 60-gallon cube that we have is painted black. And actually, Marcos Ignacio says, did you guys test with the different background colors? Aha! Just wrapped up that test. Just shot that video, and we're going to have that next week. The difference between, all right, so if we notice that black absorbs light and black absorbs spectrum, what is it? What if we have a no painted tank? What if we have a tank with a mirrored back? What if it was white? What if it was light blue? What if it was medium blue? What if it was dark blue? Tested all of those.
So one of the ideas I had in here, why we tested like a few different shades of
blue, yeah,
was, all right, so we've heard this before, but do you know why the reason why a leaf looks green? And it's because it's reflecting the green light from the sun back at your eye, and it's actually absorbing the rest, right? So what if we took like a deep blue color and painted it blue? Would it absorb the other bits of light, but reflect par back in the tank?
Most of the par comes from that blue spectrum, right?
Yeah.
400 to 460.
So maybe not total brightness, but would it reflect par back in? Would it then dark blue perform just as good as white? You guys are going to find out.
It's really cool.
Very
what we find out is really cool.
But you know what? This one was actually surprising to me in a way that I shouldn't have been surprised, because we already knew that painting the back of the tank black was dramatically lowering the par numbers.
Yeah,
right?
and we mentioned it in all of the Investigates video. Well, you just say, hey, notice at the back wall, it's because the tank is painted black. I've answered that question so many times.
So here's the piece, though.
Yeah.
If I thought that the light was reflecting off the inside of the glass and bouncing out, why would painting the black matter?
Yeah.
Should have connected the dots that it's actually reflecting off of the trends going through the glass and refracting off the next edge. Yeah, because that's the only way that painting it black would have any effect. And there's no question it has
an effect. There's a percentage of par lost in the back when you do that.
All right, so the next one here, I could have been wrong here, but I don't think the tank size has too much effect on the reflection and making or does it have too much to make it useful? We don't have the same size tank. Actually, we kind of already talked about this again.
Yeah.
So yes, changing the tank size matters, but it doesn't mean we have to go back to the absolute worst option either.
Exactly.
So,
all right.
Eyes versus par meter.
The crappy eye meter.
Yeah, okay. I'm going to tell you this part, I got another pet peeve here. And this is like how few people use a par meter to set this up. And for some reason, will spend, many people spend anything from a few $100 to a few $1,000s to buy these lights to, for the hope of doing the best we possibly can for these animals so that they look the best, grow the fastest, and we achieve our dreams. We'll spend all that money and time, all the research on it, And then when it goes time to set them up, just flip the switches until it looks good and walk away.
It's like adjust your lights based off of your coral. Are they turning pale and dying? Then lower it. Are they turning brown and dying? Then increase it. Like the bar is not dying, and that's that's like to the very edge of you are bringing them to the brink of death before you're like, oh, I should probably change that.
Okay, and so this is actually another pet peeve. Is the reality of this is you'll see a lot of people say, raise their hand, like, yeah, I flipped the switches and I was able to guess and my tank's doing really well. Well, here's the problem, man. Bravo, you were one of the chunk of people that were able to guess. Maybe you had some help, like you watched one of Randy's videos, which kind of got you close to begin with. But here, or you maybe had a friend that got you close or a general idea, but most people would not buy an $800 light and then turn it up to 30%. And that might actually be the number that you need, depending on what you're trying to put in this thing. All right, so here's the problem though, is it's how could you possibly know about the failures? Because the failures killed everything and they're gone. They're not here to raise their hand anymore. And so they're not properly represented in this equation, and most of them are probably fairly embarrassed. I spent a fortune on this tank, I bought all these corals and I killed them all. F this hobby, I'm out. I'm certainly not hanging around to tell everybody about my failure.
No.
But there's a solution to this, which is called a par meter and some windows, and you can just be done with this conversation. I know I'm in that range. Par and lighting will never be my problem. Will never be the reason I fail.
And okay, so that leads straight to the first comment here. So par meters can solve this. We used to rent par meters. We don't anymore. So the guy, or the person here says, how about we make it a 7-day rental for $50 again? $100 seems insane. And why does anybody need a par meter for 2 months?
Okay, so good question. So for those who don't know, we used to rent par meters. We decided it's just ridiculous to ask somebody to buy $500 par meter. Maybe somebody else says it isn't ridiculous. I feel like it's ridiculous.
$500. To use it for a couple times.
$1,000 on your light, you're going to use it $500 once. And then there's these other solutions. I guess you could get one for your coral club or a reef club. But then I have to be part of a club. I have to go get there. I have to wait for Jerry to be done with it. Blah blah blah. I just want to set up his tank, man.
Yeah,
and I don't want to spend $500 on something we use once. So we did this rental thing, and the problem with the rental thing of 7 days is so many people ended up into it for 5 weeks, and then it got way more expensive than $50. The other problem of it is all of a sudden we have to have all these rental agreements, and you have to have all these processes for internally, and each state's got its own rules about rental stuff, and it was just a total nightmare.
Yeah, logistically.
And I'm responsible for the new world, which is, how about instead of using it for a week, we just change the world and say, you can return it, even if you used it. So use the thing for 2 months.
If you want to.
Tweak your lights, get them set up, tweak it, do whatever you want to do. Take 2 months, let the rock work get dirty in that time. The sand is no longer brilliant white. You can adjust, you can do whatever you want. Take 2 months to get this lighting you set up perfect. Send it back to us. Doesn't matter you used it.
Yeah.
As long as it's not broken or damaged. Yeah. And 20% restocking fee, which is $100, man. But you got to use it for 2 months. I don't know. I thought it was a great deal. And then on top of that, those ones open box. If you're like, oh, these guys are getting rich off this $100. No, we're putting them in open box. You can buy it at $100 off to the next person. So actually, we made nothing, and I shouldn't say that out loud because Bob is going to kill me. But the whole goal here is let's start measuring this stuff. My pet peeve. Don't sell a $1,000 light and then leave you high and dry. You can't do the application with it.
Yes.
All right. So that's why we switched from the rental thing to use it for 2 months and send it back if you want.
Awesome.
Just trying to help everybody be successful with it. Next one.
I versus par.
So just for reference point, the people that didn't see this, what we did is we collected.
Which is fun, actually.
Was it 5 or 6?
There was 5 individuals.
took 5 people here and we asked them to do 2 tasks.
6 pros is what
6
name.
pros.
6 pros.
Six pros here, like are the best of the best here, including one of them which actually sets up or tests all of the lights for Investigates.
So Brent, who tests every single light that's out there, he should have an idea of like what par is from a light by his own eye.
I guess a lot of them within 5% or 5 par.
Yeah. We've got Jen, who has been doing this for 25, 26 plus years and setting up tanks and maintaining tanks and adjusting lights. Then you have like Jason, who had one of the best tanks here. Mark, who has one of the best tanks currently here. Adam, who is kind of, he's familiar with the par meter, has used a couple times before.
Various skill sets.
And then Josh, who actually took care of the tanks so that these lights were set up on.
Actually set him up himself.
Yeah,
right?
He set these lights. So now, without a par meter, what is the par at this spot, at this like blue spectrum, white spectrum, whatever?
So here's the moral of the story.
Yeah.
If these guys can't do it, everybody else is screwed. Like it's just pure luck after that, right? And so unless you're some super pro, if you count yourself in the super pro category, I'll give you a different credit. But if I just bought these lights for the first time, if these guys can't do it, who can?
Yeah.
And their answer was, we walked them in, we set the lights up and said, what's the par? Actually, Brent was able to do it really, really good.
Was the best at guessing.
Yeah, guessing them. He was terrible at setting them up, though, because the second test was actually, here's the keys to the kingdom. You now have a reference point. You know that there are 4 XR30s on top of the 750. You know about where these the sliders probably should be. Set it up to LPS zone, SPS zone.
Set this light between 75 and 150 par. Go.
Couldn't do it.
Couldn't do it. Not even close.
No, I couldn't do it. And in fact, I think it was like 70% of all of the guesses and setups were wrong.
Yeah. Overall.
From this crew, right?
These are pros.
Okay.
All right.
Okay. You know what? I'm going to let a secret out. So we like to give you a little bit of insider action.
Yeah.
Why didn't Randy and Ryan take guesses?
Because I don't want to be wrong.
I didn't want to look like I didn't want to look like a total idiot. Because I would have guessed totally bad.
We would have done it too.
It's so funny.
I would even say that these guys are probably better at it because they test lights for a living.
I do this. I've been doing it for 17 years, man. And I know, man, that the human eye autocorrects for light. I know that the blue light, and it's funny actually because the more you know, actually the guesses and the setups got worse, or the setups actually got worse, because I know that par is blue light, and blue light looks way dimmer. The cones of the eye represent blue light as way, way darker than green light. It's like 5x. So it's going to take 5 times as much blue light to look as bright as green light. I know all that, and it was interesting because one of the reasons that Brent failed this test so bad as setup is he forgot that there were diffusers on the radions. And when he was setting it up, he knew the tool so well. He knew what radions should be and what they are because he does this for a living. Yeah. But he forgot to account for the 25% or so that the diffusers take out. And so even with the knowledge, you can make a slip up pretty damn easy. Yeah, it's pretty interesting.
All right, so some of the other questions that came out of eyes versus par and how crappy your eyes are. You should, Pat Sorsox says, you should do a video where folks set the par over time based on coral reaction. This is how most folks without a par meter or lux meters would set lights. Then let it run for a few weeks, measure the par at the end, see what the coral par values were throughout the tank, and see if they're in line with today's recommendations for coral types, being 300 for SPS, 150 for LPS, low light softies, blah, blah, blah. Put that very common approach to the test.
Okay, there's 2 angles on this.
One is, that's how it's been done, and if we just showed you by 6 pros can't do it can't do it by eye, we also made mention that death on either extreme, too high or too low, should not be the bar. This is kind of like a step backwards if we were to test this.
So there's 2 steps here. The way that we develop the 150 or the 250, or 200 to 350 in par for LPS or SPS, and then 75 to 150 for LPS was twofold. One, we took all of the tanks here that were the most successful and measured them. Then we went to WWC, and they told us the zones that they shoot for in all their tanks. They do this for a living, looking for optimal growth, because growth means money, in a commercial setting. And they they agreed that range was what they're looking for. And then I found an article from Dana Riddle, who goes around and he tests PAR in a variety of people's tanks and takes measurements of what corals are at different levels. And he found that it was in this window where all the corals were the most successful. So, basically what we've done is what Pedersox here is talking about. It's already been done. Is by mixing our experience here. It's been with Worldwide, and then all of the thousands of par meter measurements that Dana's taken as well. So that's kind of already done. But to get to the point of what he's talking about, though, is the way that most people that are setting these things up, you don't use a par meter, is you turn the lights on, then you watch and see what happens. Basically what that means is I'm going to turn it on and I'll make changes if I'm killing the organism. Because that's what it's going to do, is it's going to show you that it doesn't like it by essentially dying.
Right.
It's going to start to retract and look ugly. You're going to deteriorate this organism's health, and you're going to have to try to nurse it back, which in many cases will lose the color, you'll lose the brilliance of the coral, and it may take a year to come back. And
it's a living organism. It's a plant. It's almost like, all right, so I bought a dog and I'm not going to do anything. Oh, he's getting skinnier. Here's an extra piece of kibble. Maybe that'll work.
It's, what it is it's a way. It was the way that we used to do, but there is a better way.
Better.
Right? And it's not a comparative, like a single coral can cost $100. So if I spend $100 on rent or buying a par meter or holding on to it for 2 months and then just returning it open box, you know what? I can save all the organisms. And more to the point, this is the part actually that I've said many times, is I get the confidence that I know lighting is not my problem. So if the corals are retracting, they look sick, I know I don't need to monkey with lighting or worry about it.
Lights isn't it.
And in fact,
not the problem.
It'd be one of the knee-jerk things that people would do is they look sick, I'll go change the lighting. But in many cases, now you just made the problem worse because you're screwing up its environment, And it's actually a different problem. So maybe it's an irritant, maybe the chemistry's off. So the value of not doing it this way, which is, doing it based on the health of the organism, intentionally deteriorating it and then changing it, hoping that it comes back. And the reality is these things thrive on stability. So the best results will be 6 months of the same, intensity. Not changing it every week or month. I'm actually more likely to keep making it look worse doing that. So it is a way, just not the recommended way.
That's true. Luke Dickey says, also here to say, please redo the Senai testing. Later models are at least 2 times any other par meter.
I threw this one in here because I've seen this now a dozen times in the last couple of weeks.
Calls to test the Senai par meter?
Okay, so we actually tested the Senai meter, and it tested it's been a long time, but we did all the par meters against each other, and I think that on average it was 15% lower. So to hear that it's now 2 times any other, we should go find out.
We should,
because
apparently it's new models or something like that. So,
well, we should go test it and
some
find
of the latest
out.
models.
Pulling up the shelf and find out, because 2 times will lead you to the wrong direction.
It's actually probably a good time to revamp that test, that whole Investigates to begin with. I don't know.
Well, it was interesting because we found out that the Lecor back then actually had a firmware
very
problem. They didn't even know about
expensive tool that some very important tests are being ran on.
Okay, we're into this
worldwide,
for
not aquariums. Yeah,
we're in this for a few grand for our purposes here, but they're using this thing all over the world, like you said.
All kinds of applications.
And they had no idea that the firmware was giving the wrong multiplier.
And here we are.
We found it out here.
We're just testing the aquarium lights in a tank.
The whole world testing these things.
And the whole world's been using that.
Randy found it.
So, all right. Reef Beta. Now doing it again with a $30 Lux meter in a Ziploc bag. Can people guess par with the help of a cheap Lux meter?
So this one has actually been top of the mind for me many years. I've never tested it because everyone says you can't use a lux meter, and I maybe get it wrong, but I think lux is basically testing brightness, where PAR is measuring photosynthetically active radiation, which are not the same thing.
Yeah.
However, like, if we could come up with like a generally accepted spectrum, you know, that most tanks are in, could you get a usable reading out of a lux meter? I don't know the answer to that question. We should try to find out.
That, that means we'd all have to have the same lighting apparatus.
But you could set up, per se, you know, using the Radion Blue Plus, you know, setting it all at max. You know, you can use this to get into range. Now you have to apply it to PAR, and it's gonna be a little wonky. But for $30,
for $30, it's better than guessing or watching the corals die and adjusting.
Okay, but he actually brings up another thing here, which is the fact that most lux meters, I haven't seen one that's waterproof sensor.
Put it in a Ziploc bag.
Put it in a Ziploc bag, and does the bag actually affect what branded bag? After $30. I think, and then all the questions in my mind. I mean, I hate to keep saying it this over, but buy it and then return it in 2 months. And just
spend $70 extra dollars.
Get 80% of your money back and go do something
confidence.
Yeah, I don't know. It looks like we got a few questions up here.
There's a couple up here before we go. James Florido says, send the effluent of the second off-gas chamber of the calcium to a GFO reactor with a ton of GFO before going into the tank. It would remove all the phosphates from the reactor and not the tank.
Okay, so I've heard that before, and like actually Eheim makes like this big chunky stuff.
Yeah.
We don't sell it anymore because nobody ever bought it. But I thought that would be a good, because GFO you generally need a tumble, but this big chunky stuff you could probably get it to flow around. The problem I thought about it is you're gonna do two things. People believe the GFO actually pulls out some of the alkalinity. And the second part of it is, are you just going to deplete that little chamber of the stuff? Is it going to turn into a big rock? I've had the same kind of thought processes. I just never tested how that works exactly. Maybe some people can chime in.
No, and I think the effectiveness, like for the 160, this running that calcium reactor with the two little fishies media in it for years, just never was phosphates just weren't a problem for us. Neither were nitrates, because that refugium we had on there was so effective. Just suck it right out. You wouldn't even notice. So pH is the problem then.
True.
Also, he asks, is the reflection similar with acrylic? Probably not.
You know what? It's going to have a totally different refractive index. So I don't know if you know, like, how it's going to bend the light. My guess, if you had to ask me to guess, I haven't tested it on an acrylic tank, whether or not you get the laser through with water or not. I don't think they have an acrylic tank.
I don't think there is.
You know what? We could probably test it on a sump here.
That, or we do have I think there's a couple frag system tanks that are in here.
Hey, you know what? Check out my Facebook. It's or Instagram. It's Ryan,
BRStv guy.
BRStv guy. After this, the very next thing we'll do is go grab the laser and we'll shoot it through either the sump of water or we'll shoot it through
an ATO
a tank.
box. Yeah.
We'll go find out. Like literally right after this is done.
We got all that stuff around here. Cool. PAR versus PER. Which one's more important?
This is like one of my other pet peeves of this conversation, right? So PER is photosynthetically usable, right, radiation, meaning that like PAR, you know, like you can get PAR radiation out of somewhat of green and some other areas.
Yeah.
Usable means usable by that specific organism. Okay, so it's a mythical creature. It doesn't really exist because like every one of these corals has
completely different.
Yeah, like come from different depths. They
the Zosendeli's not the same.
Different reflective pigments, different fluorescent reflective pigments. They've adapted to different light. Like, it's like, you know, the PER thing kind of comes out like a little bit of a knowledge flex. Like, you guys are still talking PAR. And like actually PAR is an interesting thing because I was talking to Jake and Jake was berating me because he's like, you got to use micromoles. Stop using the phrase PAR because when you use the word 450 PAR, it's like saying 450 temperature.
Instead of degrees?
Yeah, degrees. I should say in parts it was 450 micromoles.
Everybody knows.
The problem is like the universe doesn't use that terminology. Science does. Is it on us to change the way that all of you talk about this subject? Maybe, but like if I start including words like micromoles, like it starts to lose a lot of people. Right?
I know.
So I don't know. But with per, it feels a little bit like the same kind of flex, like knowledge flex of, like, yes, there is this piece, man. There is a perfect range of photosynthetically usable radiation for each specific organism, whether it be a plant, it could be my weeping willow tree, it could be my tomato plant, it could be the coral, and they're all going to be different, and it's going to be different probably for the orange coral than it would be for the dark blue coral. It'll be different for the LPS coral that's coming from 30 feet down or more, and then the coral is sitting there under 12 inches of water in a tidal area. So it's a concept to think about, but like, the per thing on the Senai is just like a red, green, and blue sensor that kind of like,
does some math, and
there's something there, but there isn't really anything there for the average reefer. For the average reefer, most of our tanks are tuned to a similar shade of blue. They're not dramatically different in most cases. And if you hit the par range, you're probably safe. Could you tweak it a little bit? Yeah.
90%, 95% if you're in the right par range and some of the, this spectrum ranges, you're going to be fine.
Actually, that'll bring up a good point. Is I got to find this article. I like, there's so many data articles, like it's just mind-boggling. But there was one where he actually went around and showed you where the most successful par range for each color of coral. So he found that, like, I'm going to make this number up because I don't remember what it was, but like oranges, he just found the most successful orange SPS at 200 par. And he found the most successful red SPS at whatever par. I got to find this article because it was awesome. I'm sure maybe next week I can find it. But you just find these different colors, coral, they can change the whole thing. And then when you look at Josh, and he told us about worldwide corals, and he's like, do we shoot for the 200 to 350 range? But like some of these corals just do better at different ends of that range.
Yeah, there's some in 400s, there's some at the bottom doing
150?
Doing great in 150.
But if you do the 80-20 on this, 80%, they'll all survive in this range. But some of them show their best color if you get either one end of that range or sometimes a little bit outside of it even. And so the way he'll do that is not adjust all the lights so you screw up the environment for everything. It's move that specific coral around to find its best coloration. And the idea here is if you're happy with the coloration of the other ones, leave them alone, for God's sake. It's the ones that don't seem to be doing well. And remember, like, give it 6 months unless the thing looks like it's literally dying. Give it some effort, and you may even want to walk it, not just dramatically change it. Walk it around and show it different environments.
Sweet.
All right. Well,
there
behind
you go.
the scenes, answer some questions.
The stuff we haven't been telling you, and the questions we haven't been answering.
Boom. All right. We'll see you next week.
See you guys.